it can only do it 30 minutes at a time. What you do here is you take the identity transformation on V, and if you want to go from beta to beta prime, you put beta here, beta prime there. Okay? And if I want to go back again, then I do the identity transformation on V from beta prime to beta. Okay? And let me just remind you, this matrix down here on the bottom, from beta prime to beta, we called that Q. And the inverse of that matrix is actually that matrix, with the two indices switched. So this one is Q inverse. So we have Q and we have Q inverse. And the idea then is that if we take Q, and which is this matrix here, we're going from beta prime to beta. So if I take V with respect to beta prime, and I apply Q to it, then I'll get the coordinate vector of V with respect to beta. Okay. On the other hand, if I use Q inverse, now Q inverse is the matrix that goes from beta to beta prime. So then if I apply beta, the beta basis coordinate vector, and apply the matrix Q inverse to it, then I'm going to get the coordinate vector with respect to beta prime. These two equations are equivalent. I'm just literally left multiplying by Q inverse on both sides. So if you want, you really only need to remember that one. Okay? So that's really the key thing that allows you to go between bases. Let's see. Although these two matrices, Q and Q inverse, look very similar, right? One of them might be a lot easier to calculate than the other. So let me just remind you, if you have I sub V from a good basis to an ugly basis, right? This is hard to calculate. Because the reason is that, okay, what do you do to find this matrix representation? You take each good vector, you do nothing to it, right? And then you take that vector and you are forced to write it as a combination of the ugly bases. Well, that's hard to do. I mean, when I say hard to do, I don't mean conceptually hard. It's just calculationally, it's messy, right? So that's not so nice to calculate. However, if you go the other way around, if you start with an ugly basis and you rewrite it using a good basis, this is easier to calculate, because now you're taking the ugly basis vectors, you're doing nothing to them, and then you're rewriting those vectors in terms of the good basis. Well, rewriting in terms of the good basis or the standard basis or the easy basis is usually simple to do, right? So you'll be able to get the columns of this one really easily. So keep in mind, I might ask you to go from here to here, which would mean use this matrix, but you might actually find this matrix by first finding this matrix and then inverting it. That would be and it might be a 2 by 2. So then you just take the 2 by 2, and you might find that the 2 by 2 matrix that I'm asking you for is messy, terrible fractions in it. But the inverse of it is very nice. Okay? You might want to, I think there was might have been a quiz question on the take-home. I think we had a take-home quiz early on. You might look back at that just to kind of refresh your memory about how that works. Okay, and then finally, 2.23, Theorem 2.23. We've talked about this one a lot. This is just how to go from one matrix representation to another. So if I have two bases, beta and beta prime, and I have a transformation with respect to each of them individually, right? Then the way you go between the two is you put Q inverse here, and you put Q here. You can make sure that these superscripts and subscripts are right. See, Q goes from beta prime to beta. So beta prime down here, beta here. These two match, right? And then Q inverse goes from beta down here to beta prime up here. Beta right here is the same as this beta right here. So these are all correct, and you get beta prime to beta prime, which is this one. So, we've seen a couple of examples. Do you remember the problem about the transformation that reflects points along the line y equals mx, or 3x, or whatever it was, right? That was a great example of a problem where that theorem is useful, because there are two bases kind of that you would want to work with for the xy plane. One of them is the standard basis, and the other one is a basis of eigenvectors for this transformation. And the basis of eigenvectors is actually the easier one to write down. It gives you a diagonal matrix. You basically diagonalize the matrix, right? But then when you want to write down the formula, what is T of AB, right? You need to rewrite the matrix representation using the standard basis, which is not the nice basis in that context. So that's a great example of using this theorem to solve a problem. So that's one that's well worth reviewing again. We did it in class, we redid it in the homework, right? These things come up that often, and I emphasize them that much. That's an important thing. Okay. Any questions on changing coordinates there? This is when we have more than one basis. We might have a nice basis, and we might have an ugly basis, and we need to be able to convert between them. We can do it. We can do it for coordinate vectors. We can do it for matrix representations. And we know sort of what's easy and what's hard about doing that, and how to hopefully do things in the easiest possible way. Okay, let's see, number 7, I'm going to talk for a little bit about diagonalize ability. Okay. Of course, we have all of these concepts for both matrices and for linear transformations. So for a linear transformation T, what does it mean for it to be diagonalizable? It just means there exists a basis, beta, right, such that the matrix representation of T with respect to beta is a diagonal matrix. So if we want to know, so if I ask you if a linear transformation is diagonalizable, this is really what it means. Is there a basis that makes the matrix representation a diagonal matrix? What would those vectors in that basis have to be in order to have a diagonal matrix representation? They'd have to be linearly independent. That actually is not necessarily true. Could fail to be, well, I'm sorry. No, that is true, but that's not quite as strong as what I wanted to hear you say. So yeah, they have to be linearly independent, because they're a basis. Yeah, anything that's a basis is linearly independent. So, sorry. It's fine. They are linearly independent, and they span the vector space V. But what's the key thing about them? If you're going to get a diagonal matrix representation, what do those vectors have to be? Eigenvectors. Yes, that's the point. They have to be eigenvectors. So again, when you take that reflecting along the line y equals mx, when you use a basis consisting of eigenvectors, then the matrix representation is a diagonal matrix. Okay? So let's just say here, beta consists of eigenvectors. How do you find the basis? Well, that's where most of the time when you want to answer questions about T, what you do is you write down any matrix representation. You write down some other matrix representation first. This gives you a square matrix. You find the eigenvalues and eigenvectors of that matrix, right? And then those eigenvectors can be rewritten. Now, of course, for a matrix, they're just going to be, a column vector. But then you have to go back and write them in terms of the basis that the standard basis that you used for the transformation t, which is going, by the way, t goes from v to v here, right? So if I get a column of numbers, it doesn't mean that beta consists of columns of numbers, right? You have to take the columns of numbers that you get here and rewrite them in terms of the basis for the vector space V. And you've done that in the homework, right? On a number of occasions. So that's kind of the basic idea there. Let me see, what else do I want to say? Oh, okay, and so then if we're doing this diagonalizability question for an n by n matrix, so if A is an n by n matrix, then what we're doing is we're looking for the existence of a matrix Q, right, such that Q inverse A Q is equal to D, and D is a matrix where the eigenvalues are going along the main diagonal. So it's going to look something like that. Okay. Let's see. So that's kind of the issue of diagonalizability. Let's see. One other point here. I wrote down at some point a test for diagonalization. So let me remind you about that. Test for diagonalization. So T is diagable if and only if. Do you remember the two conditions here? The first one was one that is never a problem if we work over the complex numbers. Right, the characteristic polynomial splits. So characteristic polynomial, let me just remind you, that's f of t equals the determinant of t minus little t I, right, splits over f. So it has to, basically just means it factors completely. It has to totally factor down. That's never going to be a problem if we work over C, because the fundamental theorem of algebra guarantees that any polynomial will factor completely over the complex numbers. So anyway, that's the first thing. It has to, because if it doesn't factor, then you can't find eigenvalues, and if you can't find eigenvalues, then you don't have any eigenvectors, and you can't do either one of these procedures, right? Okay, and does anybody remember what the second condition was? So suppose you get all the eigenvalues. What else does it take for the matrix to be diagonalizable? Right, every eigenvalue that we have has to pull its weight, and the way we would phrase that is just that the dimension of the eigenspace E sub lambda, right, has to equal the algebraic multiplicity of the eigenvalue, that's m sub lambda, and this would be for each lambda. So for every eigenvalue, that eigenspace has to pull its weight. Okay? So far so good? Let me come back over here again. I'm trying to only use these first two boards. So you basically have to take each eigenvalue and calculate a basis for the eigenspace, right? Which is just the size of that basis is what's going to determine whether this equation is satisfied. Okay. Let's see, a couple of facts that are relevant to that second point there about the eigenvalues pulling their weight. A couple of facts here. These are worth knowing. Theorem 5.5 is one of them. Let me write down what that said. Theorem 5.5 just says that if lambda 1, lambda 2, dot, 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 up to lambda k are distinct eigenvalues, the corresponding eigenvectors, I won't write out all those words, but I'll just simply write the set v1, v2 up to vk. So if I find eigenvectors that correspond to distinct eigenvalues, then what do you know about those vectors? Say again? They are Li, exactly. This set is linearly independent, exactly right. I really like the proof of that theorem. I may not ask you to prove it in a full generality now, but I do think if you look at the sample test, I asked the class last time I taught it to do it for k equals 2. So that'd be good practice. Practice testing linear independence, practice the definition of eigenvalue, eigenvectors, and so on. So that sort of thing is actually not that hard to show. Then a corollary of that theorem is that if T has n distinct eigenvalues, and the dimension of V is equal to n, so the dimension is n, the characteristic polynomial splits, you get n different lambdas, then what do you know about T? Right. T is already, without even doing any other work, without even looking at the eigenspaces, it's already diagonalizable, right? And that's because if the eigenvalues are all distinct, then these numbers are all going to be 1. And every eigenspace is at least one-dimensional. So you'll never have a problem with that. Finally, another fact kind of along the same lines of all this other stuff, Theorem 5.7, this one says that the dimension of any eigenspace is always at most, it's at most the algebraic multiplicity of the eigenvalue. So no eigenvalue can overpull its weight. That's just not possible. So if there is an eigenvalue that fails this equation, you cannot hope for another eigenvalue to make up the slack. It's not going to happen. So this is either an equality or it's the dimension of the eigenspace. By the way, this is often called the geometric multiplicity. So the geometric multiplicity is always less than or equal to the algebraic multiplicity. So when you're talking about those concepts, those are the relationships. And in order for the transformation to be diagonalizable, you must have equality across the theorem.
Can you give an example
of what?
Where that wouldn't work, where it's, let's say it's more than, the dimension of the eigenspace is more than
Than this?
Yeah.
It can't. That's what this theorem says. The theorem says you can't have that. You must, the dimension, the geometric multiplicity cannot exceed the algebraic multiplicity. So I can't give you an example of that.
Okay.
Maybe you're thinking you want me to give you an example where there's a strict inequality there? Or, because I can't give you an example where there's a multiplicity of 1 here and I get a 2-dimensional eigenspace. That's my whole point, is that cannot happen.
Okay.
All right, is that okay? Mm-hmm. Okay, great. All right, I'm almost done with my rather extended review here. That's okay. Just a couple more things to go over, and then we'll solve some problems. Everybody's up for that. Wake everybody up here a little bit. Number 8. This is generalized eigenspaces. The generalized eigenvalues and eigenvectors. So this is, these are the case of lambda. Okay, so you might remember that. We've been doing this more recently now. The generalized eigenspaces. So the first thing about the generalized eigenspaces is that the dimension of the generalized eigenspace does match the algebraic multiplicity. So even though the regular eigenspace might be too small, could be less than the algebraic multiplicity, this one will be an equality. So one way to say if a matrix is diagonalizable or not is just that the dimension of k sub lambda is the same as the dimension of e sub lambda. Because if e sub lambda and k sub lambda are the same, then each eigenvalue is actually pulling its weight. Right? In that case, the geometric and algebraic multiplicities of each eigenvalue would agree. So this is the first fact right here. If you are allowing generalized eigenvectors to be part of your considerations, then you will be able to come up with enough of those to pull a full basis of eigenvectors. But they might be generalized eigenvectors. The way that you want to be constructing these generalized eigenvectors in case of lambda, for the purposes of writing down a Jordan canonical form, for example, is by using cycles of generalized eigenvectors. So let me remind you about those. Cycles of generalized eigenvectors. So we usually use a gamma for this. And the way it would look would be over here you start with v on the right. You choose this one. You choose the first vector that you're going to work with, and then you kind of hop from right to left, and essentially you keep applying t minus lambda I to that vector, or a minus lambda I if it's a matrix. Okay, so we can do this for matrices or for transformations. The last power of t minus lambda I that the vector v survives is called the p minus 1 power. And so this is a cycle of length p. So there are p vectors there. And the idea is then that t minus lambda I to the next power, which is the pth power, actually becomes 0. Okay? Actually becomes 0 at that point. Now, that might not be the whole basis for the entire vector space V. But it's some of the basis, and therefore this will give rise to a Jordan block, if you remember. So there'll be a Jordan block, J sub lambda, basically looks like this. You have lambda going down the main diagonal, you have 1s on the super diagonal, and 0s everywhere else. Okay? But this is just one block. Right? So there could be other blocks that correspond to other cycles. And actually a cycle of length 1 would just give me a 1 by 1 block, and that would correspond to a cycle that had only an eigenvector in it. Remember that this last term here, this is a true eigenvector. That's a true eigenvector. So if all of your cycles of generalized eigenvectors have length 1, well, then you have just you have a diagonalizable linear transformation, because you only have, if you have a 1 by 1 block, do you have any 1s on the super diagonal? No. So in that case, it's just diagonal. There's no 1s above the main diagonal. Okay, here are the two important things. You know, knew that I would make sure this comes into the review. This is very important. This is going to be on the test, guaranteed, that you need to know that the number of cycles, right, which is equal to the number of Jordan blocks, is equal to the dimension of E sub lambda. Very, very important fact. Okay, so in other words, maybe you have an eigenvalue that doesn't pull its weight, but it does produce some eigenvectors, right? Some linearly independent eigenvectors over here. However many linearly independent eigenvectors you have, that's how many blocks you're going to have. Because each block, here's my block, corresponds to one cycle, right? Each block corresponds to a cycle, and each cycle has how many true eigenvectors in it? 1. So this is a 1 for 1 for 1 correspondence here. Okay? So that tells you how many blocks you have, and then how big are your blocks. That's the size of a Jordan block. Size of Jordan block. And that would be literally just the length of the corresponding cycle. So you look at those cycles, and that pretty much tells you what you have there. Okay, we all right with that? Okay, and the last point, number 9, then. Oh, and I guess sorry, let me say one more thing here. So then, of course, you're going to build your matrix Q. As usual, the columns of Q are going to be organized with your generalized eigenvectors in those columns, and they have to be arranged in the same order. Keep track of the order. Everybody's been doing a real good job of that. And then if you calculate Q inverse AQ, you actually will get the Jordan canonical form J, which just consists of these various Jordan blocks going down the diagonal. Does that make some sense? Okay. The last little bit here, I'm just going to squeeze this onto the sideboard, would be applications. And there are really 2 of these that kind of stick out in my mind anyway. The first one is the Markov processes. Markov processes. Key thing there is you've got to find the transition matrix, so as it's called, which is just this matrix A. You need to that's the matrix that tells you how to go from the current state of the Markov system to the next state. So it might be the next day, the next week, the next decade, whatever it is, depending on the problem. This matrix will model it for you. So this is called the transition matrix. Right? And one thing that will help you to make sure that you're doing the transition matrix correctly, I should have probably brought this out sooner, but I'm going to say it now, which is that the columns have to add up to 1. This is usually a bunch of percentages, right? You get these various percentages. They must add up to 1. So the columns sum to 1. Right? And what you really want to do is you want to calculate a to the infinity of some initial, so this would be like the initial distribution, initial condition, and you just want to take every time you apply capital A to that vector, you are moving one more stage forward in the Markov process. So if you do that till the end of time, infinitely many times, you'll find out the final terminal behavior of that Markov system and what the final percentages are. Okay, and of course the A is just Q d Q inverse to the infinity of V, because you diagonalize the matrix, if you remember that. Now this is going to be a little hard for me to ask you to do on the test unless it's a 2 by 2, because you're going to be diagonalizing a matrix that's got a bunch of decimals in it. And so just even finding the lambdas and all that stuff gets very difficult if it's a larger matrix. So at least from a practical point of view, it may not be that easy. However, this calculation isn't too bad. The first Q comes out in front, and then you have d to the infinity, and then Q inverse, and then all of that applied to V. So the point there is that if you write out Q d Q inverse times Q d Q inverse times Q d Q inverse over and over again, most of the Q inverses cancel in the middle, and the only place where you're really doing a big calculation is d to the infinity. But that's a diagonal matrix, so it's actually not too hard to find an infinite power of that. You just take the infinite powers of all of the diagonal entries. Okay? So that's kind of what you come up with. But again, if it's more than a 2 by 2, even finding Q inverse now is a, you have to find the inverse of a 3 by 3.